And yes, I do believe that Beyonce is the greatest country artist, not only of this year, but of all time ever. When I think country music, I think Beyonce Knowles. All right. That's not true. Sorry.
No, no, no. No, I'm not calling you the boy.
I know, right? Okay, today we're doing 4.4. And historically, this has been a couple days. Do you guys feel as though we've been going like insanely fast, or does it feel okay paced? If you've missed a bunch of days, you probably do not feel like it's an okay pace, but that happens. I'm not like faulting you for it. Every time we've done anything trig related so far this year, pretty much every triangle we've ever drawn has been in which quadrant? The first quadrant, which means we've always had an angle theta that wound up being acute. As long as you think of theta as the one that's formed between the x-axis and any amount of rotation, we always do have that nice acute angle. Now, on the unit circle, I use terminology to remember how to draw the triangles all the time. It's, what's the goofy phrase that I say over and over and over? Bow ties and butterflies. So the reason why I'm so hardcore and why I stress it so much is going to become hopefully evident today. We're going to be looking like trig angles or trig functions for any angle. Now, right off the bat, we have a few ways that we've already defined sine and cosine. I know that the sine of an angle theta is the ratio of the opposite side length over the hypotenuse. And I use SOHCAHTOA when I'm thinking that out. Now, if you can recall, we had other ways to define it. So you do not have to write this one down. I'm going to do it in green over here. In this box is just my scratch work. I want you guys to give me another way to define this. I know that sine of theta can be the opposite side. And again, you do not have to write this unless you want to. In this box is my scratch work. Give me another way to define sine, rather than using the SOHCAHTOA idea. There's one more way that we looked at it. So I heard a bunch of them. It could be 1 over cosecant. I love it. That's a reciprocal identity. Any other ways? I heard it over there. Y over R was the alternative. Now, if you give me any right triangle, especially in quadrant 1, the Y is the opposite side from that angle theta, and the R is the radius, right? So these definitions, they look wildly different, but are they really different? No, we're just changing the language that we use. And it turns out that that is super duper convenient. And what that's going to allow us to do is a bunch of new problems that we can make a little bit simpler. So we already have the definitions here. Let's just go ahead and do a quick recall. And we'll just say defining trig with x, y, and r. And I know that this is something that you already have written down, but I promise writing it down again will not impact you in a negative way. Not even a little bit. We're going to make sure that we have these trig, I said trip. It's not fall. Weird. I don't even know how I can save that one. Boom. Defining trig with x, y, and r. And we've already done this, but I want to make sure that we can work this out. Now, we have a few of these: sine theta, cos theta, and tan theta. These are the three main ones that we always start with because the reciprocals are on the other side. Only using x's, y's, and r's. We've already seen, Rafa reminded us that sine is y over r. What's cosine? X over r. And tangent? Y over x. Now, I'm not going to require you to write these right now, but I want to make sure we have it. If you want to, you can put it, because again, it won't hurt to write it down again. But if sine is written here, what do we put next to sine when I'm writing all these out? Cosecant. And how would you find cosecant theta? R over y. Now, the second we do this, we have a caveat that we must pay attention to. A special little consideration that might make this more clear. This could break stuff. Like the whole world could explode if you're not careful here. Because what might you do for some y value? You could divide by 0. Can we ever let it be 0? So because we can't, we include this caveat pretty regularly. What goes next to cosine? Secant, and that's because they're reciprocals, right? 1 over cosine is a reciprocal, and it gives us what we call this secant function, where it's just r over x. What's my caveat?
So what if it is 0?
Then it's undefined.
Oh, that
Yep.
Just write that.
Yep, there's no answer because it doesn't even make sense to do because we can't divide by 0 unless we're in calculus. And even then, that's kind of a general statement. Okay, should there have been a caveat on tangent?
Yeah.
What can't be 0 in tangent? Try again. In tangent, I don't care if the numerator is 0. X can't be 0. The denominator is the only thing I'm really worried about. And for cotangent, I know that it's x over y, and we run into that same, hey, let's just make sure that y is not 0. Okay, nothing crazy about these. We've already seen this, you already have them. What we're doing today and where our extension is going to happen from what we've already seen is that before we were only in quadrant 1. It turns out, however, and I'm not going to draw it, you don't have to draw it because I'll draw a nicer one here in a minute, but that works really nicely if I put that angle anywhere in here. If I get over here, stuff starts to feel a little bit different. This is my angle theta. And all of a sudden, you start to think, well, how do I make a right triangle out of that? And you guys already know that the bow ties and butterflies exist because I stress it like crazy. But if we didn't, notice all the different options that somebody might have to try to draw this right triangle. And without having some sort of consistency, we're all going to get wonky work that's not going to quite agree with everybody else. Okay, this is the importance of it. Now, we are starting today fresh. It's a Monday. We're going to do one example problem before we jump into new stuff, just to make sure that we can recall the stuff that we've already seen. So, essentially a warm-up, I suppose. Our first example is, I'm going to word this very mathematically. We're going to be given a little bit of stuff, and let's see which one we want. I'm going to let the point -2, 3 be on a circle. I'm fine with that. Now, just language-wise, on a circle is very different than in the circle. On means you're on the circumference, somewhere along the outside. So we're already thinking about circle. We have this point is on some circle. What I want us to do is, if theta passes through, and we'll be more, I'll clean this up a little bit. If theta passes through that point, well then, I want us to find sine, cosine, and tangent of theta. Find sine, cos, and tan of theta. Now, a little bit of weird language here that we're going to work out, but I'll wait until everybody gets it written down. Before I just tell you that it's weird, I want you guys to do me a favor. It doesn't have to be perfect to scale, but it should be roughly okay. I want you to draw me the angle theta on your page. You should use a coordinate plane, which means I want to see the origin in it, but show me the angle that I'm talking about and see if we all agree before I just say, let me explain it. So as I look over people's shoulders, I see this, which is a good start. And then I'm seeing it without any scale given. Here's my point, -2, 3. Now, anytime we're talking about an angle, unless I specify something very specific and different, I assume that the initial side is always where? Positive x-axis. So, as I'm looking at it, when I say that the angle runs through this point, I don't care if it goes to here or if this thing goes forever. It doesn't matter to me. The picture's going to be nicer if I stop there, but I don't have to. This is where I naturally want to stop. And here is my angle theta. That is some angle that spits out that. Now, just to highlight, and I don't want you guys to draw this second part. I'll do this in purple, I guess. I think that's purple. If I had gone further, it looks dumb, but can I still draw a triangle here if I wanted? And it looks odd because I have that side sticking out further, but it's the same picture. Okay, from this, if we hadn't mentioned bow ties and butterflies, you run into that weird situation that we just discussed. Now, does the picture help? Do you think we could do it without the picture? What do you think, Riley? Let's try it. Like, I have the picture, I'm not going to erase it, but I just want to note and you guys to see just how nice these can be. The pictures are really nice if you have like an applied problem where you have to make sense of stuff, but we don't need it. We don't need it at all. Looking at this, can you tell me the x value that this side of the triangle would have? -2. Now, I know that it's truly a distance to be positive. I just went -2 from the origin, right? And y is 3. Hardest part here. How do you find the radius? One more time. The hypotenuse. Now, two ways to think about this. Because I'm trying to make us think without the picture, I could draw the triangle and say, let's Pythagorean theorem. Or we could just think about what the Pythagorean theorem actually comes from. The Pythagorean theorem is just a distance between these. What's one of my points? 0, 0, right? That's the other one. And then the other side is at -2, 3. Well, can we imagine with x and y without physically drawing it that x squared plus y squared is r squared? And I know that relationship will always hold true. It's the Pythagorean theorem. Or if you'd rather, I wouldn't do this, but you could certainly think about the distance between 0, just like this. Gosh, what formula did I just use? It's the distance formula. But I would never advocate for the distance formula here in true form because do these zeros really do anything for me? So let's cut out the whole distance formula, but we see that, hey, we can do this without the picture. I think that r is always going to be the square root of x squared plus y squared. Like that's what my Pythagorean theorem is always going to spit out, or the distance formula always if 0, 0 is a point. Which means in this particular problem, let's just check it out. What's -2 squared? 4 plus what's 3 squared? And I think I'm comfortable, if you guys are, I'll continue r's here. I think just root 13. And nothing else changes, right? Now, could we have done this without the picture? And I didn't even really use the picture other than to make you guys practice drawing it. You think you could do this without the picture? As soon as I have x and y and r, check it out. We have everything defined already. With just having x and y and r and nothing else. I'm not even going to look at the picture. I know that sine of theta is y over r. What did we just find y was? So 3 over root 13. And I don't like that. I'm going to fix it. When I rationalize here, we need honesty. Did I lose anybody in how I did this rationalization? Okay. You do not, if you can do this in your head without showing anything else, I'm good with it. When I'm talking about rationalizing, all I mean is let's make it so there's no square root, an irrational number in the denominator. So we're trying to make the denominator rational. I can only ever multiply by what without changing stuff? 1. And it turns out in this case, I'm going to use the square root of 13 because root 13 times root 13 is 13. That's now a rational number, hence the rationalizing word. And here we go. 3 root 13 over 13. Never had to take a look at the triangle, didn't have to think about it. It exists and it's fine, but I don't need it. Okay, I want you guys knock out cos theta and tan theta without ever looking and drawing anything on your triangle. Only using the definitions that we have. I'm going to give you a moment. I'm only going to write the rationalized answers here. Yes, you're just kind of annoying. Like, and honestly, I don't care. It's up to you. In all reality, this drives me crazy. If it doesn't you, that's fine. I hate it. It's kind of annoying. Kind of annoying. Anybody else do it? Want me to comment on how I feel about it? Anybody else keep the negatives in the denominator? Barsega, is that a yes? Ask me how I feel about it. It's kind of annoying. All right. It's fine. Really, you can keep the answers that way. Cool. Doable. Yeah? Baller. Now, there is a huge issue that occurs as we're looking at these things, though. If I just use the definitions, it's very clear when things come out positive and negative. Now, in contrast with that, I'm not going to wear my hat for now. There are some things that we do and that we can do if we want to use these triangles that are completely fine. We just have to be able to account for them. So, when we're looking at these, oftentimes it's easier to think of an acute angle, I think. If I asked you for the sine of 30 degrees, without looking at your cheat sheets, can you get it for me? Sine of 30. It's either, so 45 is my root 2 over 2. So it's either root 3 over 2 or it's either 1/2, one of those. So I heard both of them. Just a little spoiler here. Check it out, 30 degrees. Am I further right or further up? I'm further right, so I know that the right number should be root 3. And what's the y value or the sine? 1/2. It's okay if you didn't get it right there. This is always going to be the logic that I use. Now, so let's just agree real quick. Sine of 30 is 1/2. Okay, easy. If I said, oh, well, what about the sine of 210? Is it a harder question? So the fact that nobody's given me the answer yet makes me think that, yes, it is a harder question. And I'll tell you, in reality, it's the same question, but you're just down here, where here's your 30 degrees. 30 is easier than 210. Yeah, we all agree, I think. Even though they're the same angle. The same triangle gets formed, it's just oriented differently. They're the same thing. But because it's so much easier and natural for everybody to think about regular acute angles, because, you know, triangles typically have them, especially right triangles, maybe from time to time there is value in just shifting it a little bit and giving ourselves nicer angles. So the second main idea in 4.4 is going to be in defining reference angles. Reference angles. Now, informally, I'm going to talk about it first here real quick. Reference angles are just the true acute angles on a triangle for any angle theta. Now, if you think about angle theta that's at 210 or whatever, then obviously you're struggling to first envision that acute triangle. However, if we use reference angles, we're going to get them. So we're going to give a little bit more formal of a definition real quick, and then we'll see that these things really aren't bad to deal with. So, jumping in, we are going to go ahead and let theta be an angle in standard position. Okay, we have an angle in standard position. And whether we've used this language like over and over or not, I just don't recall. When I say an angle's in standard position, it starts from where? Positive x-axis. That's all we mean. It just starts at the positive x-axis, and then it starts rotating counterclockwise if it's a positive angle or clockwise if it's a negative angle. So we have some angle. Doesn't matter. Any angle. We're going to say the reference angle, or and I'm going to even change that, the acute angle between, and I need your guys' input as to how wordy we make this. Nope, I lied. I'm just going to make it wordy. The acute angle between the terminal side of theta, which terminal, remember, just means ending, so it's where we end. The acute angle between the terminal side of theta and the x-axis is the reference angle. And that sounded like there's a period there, but I'm going to add one more little piece. So all of a sudden, right off the bat, bow ties, butterflies. That's the wordy version of that. You got a new one. Cool. Cool. I play with the one at my house a lot more than I thought I would. Like, yeah. It's too cold. All right, anyway. We have an angle theta, wherever it is. If you take the terminal side of it, and then you make the angle between that and the x-axis, you get this reference angle, denoted, which just means how we write it. And this language is going to show up again in future stuff. Theta prime. And we just use a single apostrophe. I'm going to write that out. You don't have to unless you need to. Theta prime. Okay. Now, the reason that we do this is because instead of thinking about the triangle formed with a 210 degree angle, which sounds like a nonsense question, we can now think of, oh, 210 degrees is just 30 degrees in this quadrant. And we're going to use this to our advantage. So what I want you guys to do for a second is just to have a nice little reference to be able, I started at the weirdest spot. Why am I, what? Okay, I'm at 50% zoom. That's an issue. Cool. Classic. I want you guys to do me a quick identifying reference angles situation. Okay, to identify reference angles, it's our bow ties and butterflies, but I want you guys to come up with a rule for how it works. Quadrant 1 is easy. Any angle theta that you give me in quadrant 1 is already acute. So whatever it is, we already have the triangle. But what we don't have is how to find these reference angles, or my theta prime, for quadrant 2, quadrant 3, or quadrant 4. Okay, what I want you guys to do, and I'm going to ask that you do this in both degrees and radians, is we're going to sketch an angle that terminates in the given quadrant. So on the blue one, maybe it's this. There's theta. Now, I'll kind of push you through the first one, but I'm going to ask that you do whatever we do on quadrant 2. I want you to extend that idea into quadrants 3 and 4, and we'll see these things are actually pretty easy to deal with. Now, did you say my name? Oh, weird. Oh. Okay. From our first picture, bow ties and butterflies is where my mind goes automatically. If I want to take this angle, it's obviously bigger than 90. It's not an acute angle, which means it's going to be hard to think about in terms of triangles. However, if I go from the terminal side here all the way to the x-axis, do you guys agree this is the angle right here? Now, just to relate to my bow ties butterflies, there's my bow tie and butterfly that we always talk about. As we're looking at this angle right here has a name, and it's something very specific. If this is theta, then the now acute angle formed between the terminal side of theta and the x-axis is called theta what? We have theta prime. That's it. It's just an apostrophe. Now, sketching it is one thing. It's nice. Weird stuff happens when you have to think about what quadrant are you in, because signs of functions change as you move around the circle. But 30 degrees is much nicer than 150, as long as you recognize that cosine is negative because of where we are. Okay, when finding these, let's say I wanted to find theta prime. We're going to do it once in degrees and once in radians. If I wanted to find theta prime in degrees, how would you find this green angle? And don't write it on yours, but let's just use some nice ones. Let's say that's 140 degrees. And this is just for me to help think it out. What do you guarantee theta prime has to be? 40, why? It adds up to 180, right? So I know it's 40. Mathematically, can you just change the order of that? What if instead of saying it's 140, I said it's just theta? How do you get theta prime? 180 degrees minus theta. It's going to give me the same thing, right? 180 minus 140 gets me to that 40 that we know that it had to have been. Or, if you prefer a realistic way to talk about angles and not some nonsense that just made up, instead of 180 degrees, I don't like degrees. How many radians? One of you said, I don't know who.
2 pi.
Ooh, 2 pi is too much. Pi radians minus, what was that original angle still? Theta. Boom. You guys, your task currently is to do the exact same thing. I want you to draw for me. I'm going to draw this one obnoxiously out far, and you'll see why, because when you draw theta prime, there's theta. And we'll do this one over here, where here's my obnoxious theta. I want you guys to do two things. On your figure, draw me theta prime, and find me how do we calculate out theta prime, both in degrees and radians. I'm going to give you a minute. You guys want to try the Bluetooth where you have to label it and I just walk around and put this on your desk? Cool, let's try it. All right, so JV hooked it up. He's got it. In quadrant 3, the only thing, I'll steal that for just a second, the only thing I want to make sure is really clear is that when we're looking at these, if I put this down on your desk, you can pick your own color over here. Don't pick white, that wouldn't work. But right here, right there, that's my theta prime. That's it. Okay, who's confident about quadrant 4? Cool. Go ahead.
Quadrant 3, why would it be pi?
Ooh, that's a great question. Where's pi halves on my unit circle? Here's 0. It's straight up, right? So if we did this angle here, and we're gonna have to look, we might have to fix this part, but that's okay. If we did, let's do the same thing we did before. Let's make this a number. I'll steal this. I'll let you do the next one. Okay? We're gonna fix this. Give me any number that theta in number 2 could believably be. Can I pretend like it's 190? Like that'd be that angle, right? Could be. If you wanted to find this, could you tell me what it is? If the whole angle is 190, why 30? Why 10? Because you just went a little bit too much past 180, right? So we're just going to switch the order around, although JV, I like where your head's at. I see the right stuff showing up. You're simply going to take your theta in this situation and subtract how much? 180 degrees. If, by contrast, we'd rather do this in radians, no different. We take our angle theta, but instead of subtracting 180 degrees, we subtract how many radians? Pi of them. That half circle. Okay, Riley, do you think you can knock out the third one? Sorry, the quadrant 4?
No, we have the same thing.
So at least draw me theta prime.
Okay.
Okay, remember this whole area is the screen. You can very clearly see where both of my writing happens. Like it wears it away.
Oh, sorry.
The very top left button is your undo. There's your undo, okay?
Okay.
Cool. So we have theta prime from the terminal side to the x-axis. It looks like, to me, the little angle, and we'll determine here in a second. Once
Right.
Kalisha finds her spot, she can mark it. I want you to mark. That works too.
Wait, don't you want me to write the things?
Draw me the angle first. Where's the reference angle theta prime in that picture?
I don't know.
So where do you think it is? Between the terminal side and the x-axis.
So right here? Just finish it. Right here, like this.
So we're all judging.
Yeah, we are.
You're good.
I'm confused. This way, it's down.
So draw it. You got it.
Are you sure?
I don't know. I can't tell until you draw it.
I'm scared.
Don't be afraid. We have an undo button. Anybody agree with that being theta prime?
Yes.
Now, the only thing, and it's not a bad thing, I don't know that I put the angle or the direction. I don't want the direction because I don't want it to be negative or positive. But I agree with you. This angle that Kalisha has just found is theta prime. Now, if we wanted to calculate it, add me a dash here.
Okay, hold on. So, where?
Oh, much better. Make this theta prime instead of theta. So you just need a apostrophe. Okay. let's say that we had some angle, 350 degrees, hypothetically. We'll use 340 so it's not the same. If this is 340, what is this blue angle?
Is prime.
So it is theta prime, but
20.
it has to be 20. How do you get there using addition and subtraction?
360 minus.
360 degrees minus theta. That's the way to do this in degrees. Felicia's going to write it for us. I don't know that we're going to do this constantly because, actually, if we do this like a week and I have you guys write on it, you think you'll be used to it?
Yeah.
Okay.
Well,
I will try to keep doing this. I'll steal it from Felicia in the interest of time for today. Oh, 360. Love it, kind of. I'm going to steal this back real quick. We're going to be really judgy. What don't I like about Felicia's formula here?
Nothing. Oh, what the? I didn't put degree.
You better tell me it's degrees. Okay, if we wanted theta prime instead in radians, only one little change. 2 pi minus theta. And we're there.
Natural.
Cool.
You're natural.
I spend a lot of time on this thing. Okay, now from here, I want one quick example, and then we're going to make tomorrow short so that you have time to work on note cards and stuff in class tomorrow for our quiz on Wednesday. Sweet. So last little piece of class today, quick example. I want you to find the reference angle. And notice I'm not calling it theta prime, and I'm doing that for a very particular reason. Cool. So on A, I'm going to have you do like 3 of these real quick. On A, let's say we have, we'll use theta here. Let's say theta is 292 degrees. I want you to find me the reference angle to angle theta. On B, let's get real crazy with it. I want alpha equals 9 pi fifths. And on C, let's go ahead and say angle beta is 3. Now, notation-wise, if you might not love it, keep the angle. Don't name it something new unless you're going to take the time to say, hey, this, look at me renaming it and physically telling you I'm renaming it. I'm going to give you a moment, and then we'll pass this around and get a little more practice with it. So on the board, we see Abigail has done 2 things. On part A, she determined that 292 degrees, without writing it down, that's completely fine. She says it's in quadrant 4. And in quadrant 4, if I have an angle in degrees, I just take theta prime as 360 minus it. So Abigail did 360 minus 292, and we find theta prime is in 68 degrees. Now, it's easier to use 68 degrees on my triangle, but you have to pay really careful attention when we start evaluating. If I said, what's the sine of 68? It's positive, because 68 degrees is in quadrant 1. Our reference angle just makes it nice for us. I know for a fact that down here at 292 degrees, this should be sine is positive or negative down here? Negative, if we're doing it. So, one thing that I would recommend doing, it's not required, but I would take just a second to go ahead and say, hey, quadrant 4 is where I'm at, because later when we have to say whether sine or tangent or cosine, whatever is positive or negative, we know where we're looking on the circle. Okay, anybody want to take the non-daunting task of writing on the board for the second one? Okay, we're going to practice on this one day. First off, 9 pi fifths. Is that quite to 2 pi? But it's really close to 2 pi, right? 10 pi. That tells me I'm in which quadrant? Yep, quadrant 4. I'm almost at 2 pi, but I'm not quite there. Now, check your pages, because I'm crazy. If the angle is alpha, what should we name the reference angle, Riley? And what do I not like about yours? I'm looking over your shoulder. Good. We're going to call it alpha prime if we're talking about angle alpha. So I'm going to take one little quick step through this. Instead of writing out the general formula here in radians, I'm just going to change some stuff. Instead of 2 pi, I'm going to think of it as 10 pi fifths. Does that still say 2 pi? Minus theta, which is 9 pi fifths. And what do we determine alpha prime is then in the end? Pi fifths. And we're done. Now, unrelated to the specific math, when I first started doing my tablet stuff, coincidentally before COVID, which made it really easy for me to transition, one of the things that I tried and people hated was standing behind the class like this and working at the board. Is it bugging anybody? Okay, I'm going to take a seat here then. All right, last one. Talk it out with your neighbors. Beta is 3. No elbows. That's a DQ if you're a UFC. All right. No, UFC. All right. Check it out. Check with your neighbors. Heated arguments are hopeful. However, if there's no degree symbol, it's always intentional. Like, I'm not trying to trick you, but I'm trying to trick you, right? Like, I'm making you pay attention. There's not a whole lot of nice numbers that show up in radians on the unit circle. They usually have pi in them. What's pi? I can't even check it because I know like 4 digits. But I think it's 3.14, 15926, 92. I'm lost. Is 3 less than 3.14? But just barely, which means I'm pretty confident that if you wanted to draw it, which you don't have to, but I think this is my angle theta. All that I care about realistically is I'm quadrant 2. Now, there are the weird situations, right? Where you have to decide is 2.5 pi, which quadrant's it in, and you have to be able to divide something by 2 to see is it greater than 0.75 or not. And there's weird places, but we're in quadrant 2, which means if we're in quadrant 2 and I want the reference angle from beta is 3, I'm going to use this formula here. So let's check it out. First off, how would you name the reference angle? Beta prime equals, and let's see, it's theta is 3 minus pi. Am I going to do anything else? If you really want to, wait a second, am I backward? I just used quadrant 4, didn't I? What? Time. We're in quadrant 2. I was looking at this because it's the second one in the list. Got me good. If I scroll up just a skosh, do we write them there? Yeah, look at that. Cool. All right, so instead of doing that, I'm going to take pi minus what? Pi minus 3, and we're done. That's it. Cool. 7 wonderfully, beta prime, 7 wonderfully marvelous minutes for you to work through the following. I will put it up on the video, so if you forget a picture or a book, I'll have to steal somebody's book here in just a second. But tonight, you get the privilege of homework 4.4.1, which is waiting for you on page 296. You get problems 15 through 25 and 45 through 51. And Kalisha, I need you to listen really carefully. Ears wide open, okay? Are your ears open? Okay, I can't tell. I like that you showed me your ears to yeah, see? Only odds. Don't do all of them. Only the odd problems. If you want to do them all, more power to you. That's awesome. You don't have to. Cool, cool, cool. I'm going to steal your book. I think we could have gotten through the entire lesson today, because I don't think that the stuff that we're doing is super hard, but for those of you in my physics class, this is more fresh than anybody who's not in physics, because we've talked at least about a little of it. All right, I'm going to use a quick screen capture, 15 through 25. What? What? There it is. Okay, there's 15 and 17 in the directions. Okay, I'm going to make a deal with you. I didn't write it down. If you can do sine, cosine, and tangent, if you legitimately believe you can do cosecant, secant, and cotangent as well, if you're comfortable with it, I'm okay if you only do the 3. I'm only going to read the sine, cosine, and tangent when we check the answers. Know that you can do the reciprocals to get the others, but I think that everybody in here can flip a fraction. Okay, there's 15 and 17. This time, all you're doing is telling me where theta lives. Love this problem. It's giving you a bunch of trig stuff. Okay, 23 through 25 is right here, where, again, sine, cosine, tangent. And they're telling you what is going on with it. So sine of theta greater than 0 just tells me I'm living in quadrant 1 or quadrant 2. If tangent's negative, I must be in quadrant 2. So I'm looking at 23 with that comment. And then I lost my other spot. It's 45 through 51. Here we are. Find a reference angle. There they are. Degree, degree, radian, radian. And then finally, the last few, use the reference angle to find the sine, the cosine, and the tangent without a calculator. You might want to use your unit circle, but they're there. Cool. 5 minutes to start. Cool. I sure hope so. Yeah, I am. I can tell because the pause in the bottom right. Thank you for me bar that. And I'm just going to say sine, cosine. And we're about to make the jump from what feels like geometry to what feels like algebra using all these stuff. When you're deciding if you should skip secant, cosecant, and cotangent, keep in mind that on a test or a quiz, I will ask you for those, but I don't think it's necessary to make you flip a fraction 40 times on an assignment. Cool.